Imagine standing on the frozen shore of Antarctica, looking out across an ice shelf that stretches beyond the curve of the Earth. The silence here is absolute. The air itself seems frozen. Beneath your feet lies ice nearly 3 miles thick. Ice that has been accumulating for hundreds of thousands of years, compressing under its own weight into a crystalline archive of ancient atmospheres. Now imagine that ice disappearing. Not over centuries, not over decades, in a single rotation of the Earth. 24 hours. 30 million cubic kilometers of ice. An amount so vast that if you could gather it all into a single block, it would tower 200 times higher than Mount Everest, transforming from solid to liquid in the span of 1 human day. The energy required would be incomprehensible. The consequences would reshape not just coastlines, but the very mechanics of our planet's climate engine. This is not a prediction. It is a thought experiment. A way to understand the fragile equilibrium that holds our world together, and what happens when that equilibrium shatters. Antarctica is Earth's coldest, driest, windiest continent. A landmass larger than the United States and Mexico combined, nearly entirely buried beneath ice. The Antarctic ice sheet covers approximately 14 million square kilometers, holding within it 68% of the planet's fresh water. According to measurements from NASA's GRACE satellites and research published in the Proceedings of the National Academy of Sciences, this frozen reservoir contains enough water to raise global sea levels by 57.2 meters, roughly 190 feet. To comprehend this scale, if you stood at the ice sheet's thickest point, you would be standing 4,900 meters above bedrock, higher than most commercial aircraft fly. The ice beneath you would have taken millennia to accumulate, each annual layer of snowfall compressing the layers below, trapping tiny bubbles of ancient atmosphere like messages in bottles from Earth's climatic past. The ice is not static. It flows. Slowly, imperceptibly, driven by its own immense weight, the ice sheet spreads outward from its center like molten glass on a window pane. Near the coasts, this flow accelerates into ice streams, rivers of frozen water moving up to 1 kilometer per year toward the surrounding ocean. These streams feed into massive ice shelves that float on the ocean surface, buttressing the ice sheet behind them. The Antarctic ice sheet exists in a delicate thermal balance. Currently, research from the Ice Sheet Mass Balance Intercomparison exercise indicates that Antarctica is losing approximately 150 gigatons of ice per year, enough to fill over 60 million Olympic swimming pools annually. This loss is concentrated in West Antarctica, particularly around glaciers with ominous names: Thwaites, Pine Island. These glaciers rest on bedrock that slopes downward inland, making them vulnerable to a phenomenon called marine ice sheet instability, a runaway process where warming ocean water triggers retreat that feeds on itself. But these losses occur gradually, over years and decades. Our scenario demands something different, something instantaneous and absolute. Let us imagine it begins at midnight, Greenwich Mean Time, on an arbitrary day. Through some catastrophic mechanism, perhaps an unprecedented geothermal pulse from beneath the continent, or an impossible alignment of atmospheric and oceanic warming, the Antarctic ice sheet begins to melt. Not gradually, but explosively. The first indication would be seismic. As ice transitions from solid to liquid, its volume decreases by approximately 9%. The sudden collapse of billions of tons of structural ice would generate vibrations detectable by seismographs worldwide. Within the first hour, monitoring stations in New Zealand, South America, and South Africa would register unprecedented seismic signatures. Not the sharp jolts of earthquakes, but sustained, rumbling disturbances emanating from the South Pole. The energy required for this transformation would be staggering. Ice has a latent heat of fusion. the energy needed to convert it from solid to liquid without changing temperature, of approximately 334 kilojoules per kilogram. For 30 million cubic kilometers of ice, with an average density of roughly 917 kilograms per cubic meter, we're discussing roughly 27.5 million cubic kilometers of pure ice mass. The energy to melt this would be approximately 9.2 times 10 to the power of 21 joules, equivalent to the total energy output of the Sun reaching Earth for about 7 months, concentrated into a single day. Where would this energy come from? In reality, nowhere. The laws of thermodynamics forbid it. But in our thought experiment, we must imagine it arriving, perhaps from Earth's interior, perhaps from some external source. The result would be catastrophic and immediate. By hour 3, vast meltwater lakes would form across the continent. The ice albedo feedback, one of climate science's most potent amplifying mechanisms, would engage with terrifying speed. Ice and snow, being white, reflect 80 to 90% of incoming solar radiation back to space. Open water, by contrast, absorbs more than 90% of it. As ice disappears, dark water would replace reflective white surfaces across 14 million square kilometers. The absorbed solar energy would accelerate the melting in a runaway feedback loop. The meltwater, initially near freezing, would begin pouring into the Southern Ocean. According to research on thermohaline circulation published in Nature Climate Change, this influx of fresh water would have profound effects on ocean density. Seawater's density depends on temperature and salinity. Cold, salty water is dense and sinks. Warm, fresh water is light and floats. The Southern Ocean drives a critical component of global ocean circulation, the formation of Antarctic bottom water, where cold, salty water sinks and flows northward along the ocean floor. 30 million cubic kilometers of fresh water entering the ocean in hours would catastrophically disrupt this process. The surface waters around Antarctica would freshen dramatically, becoming too buoyant to sink. The formation of Antarctic bottom water would cease. Simultaneously, the Atlantic Meridional Overturning Circulation, the AMOC, often called the ocean's conveyor belt, would face unprecedented stress. Research from Woods Hole Oceanographic Institution indicates that the AMOC carries up to 25% of the total heat toward the northern hemisphere. Antarctic meltwater, traveling through interconnected ocean basins, would reduce the salinity of the North Atlantic, potentially causing the AMOC to slow or collapse. At the 24-hour mark, Antarctica's ice is gone. In its place, an exposed continent. Bedrock shaped by the weight of vanished ice into a massive bowl, parts of which lie below sea level. Above this newly revealed land, the atmosphere churns with unprecedented energy. The latent heat released by the melting ice would warm the surrounding air, creating thermal gradients that spawn superstorm systems. But the most immediate, visceral consequence would be felt thousands of kilometers away, on every coast of every continent. 30 million cubic kilometers of water spreading across the world's oceans. Earth's oceans cover approximately 361 million square kilometers. Simple division suggests the water would raise sea levels by roughly 83 meters. But accounting for the actual volume calculations and the displacement that already floating ice shelves contributed, research from the National Snow and Ice Data Center confirms the figure. Global mean sea level would rise approximately 58 meters, 190 feet. This is not a gentle rising tide. It is a tsunami in slow motion, a relentless wall of water that arrives over hours, submerging everything in its path. In Miami, where much of the city sits less than 2 meters above sea level, the entire metropolitan area would disappear beneath 58 meters of ocean. South Beach, the Art Deco district, the towering condominiums of Brickell Avenue, all submerged. The city would become an underwater archaeological site, buildings standing like artificial reefs in the new coastal geography. New York City would fare little better. Lower Manhattan, home to Wall Street, the 9/11 Memorial, the Brooklyn Bridge, all would be underwater. The Statue of Liberty would stand with water reaching her waist. The phenomenon would repeat in every coastal city. Shanghai's glittering skyline submerged to the 15th floor of its buildings. London's Thames Barrier, designed to protect against storm surges, rendered laughably inadequate as water overtopped it by 50 meters. Bangkok, Ho Chi Minh City, Kolkata, cities where hundreds of millions live, becoming shallow seas, dotted with the tops of the tallest structures. According to data compiled on sea level rise impacts, approximately 230 million people currently live within 1 meter of present sea level. Nearly 1 billion live within 10 meters. At 58 meters of rise, virtually every major coastal city would be partially or completely submerged. Entire island nations, the Maldives, Kiribati, Tuvalu, would vanish entirely from the map. The geographic reconfiguration would be biblical in scale. But the water itself is only the first-order effect. The second-order effects would reshape Earth's climate system fundamentally. With the AMOC disrupted or collapsed, northwestern Europe, warmed for millennia by the Gulf Stream and North Atlantic Current, would experience rapid cooling. London, at the same latitude as Labrador, would see temperatures drop toward those of subarctic Canada. Meanwhile, the southern hemisphere would warm as heat ceased to be transported northward. The tropical Atlantic, deprived of the mixing effect of the AMOC, would become stagnant and warmer. The disruption of Antarctic bottom water formation would starve the deep ocean of oxygen. Nutrients that normally upwell from the depths, feeding phytoplankton that form the base of marine food webs, would remain locked in the abyss. A massive die-off of marine life would ensue. Dead zones would spread across the ocean floor. The ocean's capacity to absorb carbon dioxide would diminish, accelerating atmospheric CO2 accumulation. On land, the newly exposed Antarctic continent would experience conditions unknown in human history. Without its ice cap, Antarctica's interior, previously elevated 3,000 to 4,000 meters above sea level by ice, would sit at or below sea level in many regions. The bedrock, compressed for millions of years, would begin rebounding upward in a geological process called isostatic adjustment. But this would take centuries. In the meantime, parts of Antarctica would be flooded by seawater. The ice albedo feedback would continue its work. Without the reflective ice covering Antarctica, the Southern Ocean would absorb vastly more solar energy. According to studies on ice albedo forcing, the loss of Antarctic ice would contribute approximately 0.6 degrees Celsius to global temperature increases through this mechanism alone. This heat would further disrupt atmospheric circulation patterns, shifting storm tracks, altering monsoon systems, and transforming regional climates worldwide. In the aftermath, humanity would face a world almost unrecognizable from the one that existed 24 hours prior. The economic cost would be incalculable. Not just the direct losses from submerged cities, though those alone would run into hundreds of trillions of dollars, but the cascading failures of global infrastructure. Ports, the arteries of global trade, would be destroyed or rendered unusable. Power plants, many located near coasts for cooling water access, would be offline. Transportation networks severed, communication cables cut. The refugee crisis would dwarf anything in recorded history. Billions of people displaced. Where would they go? The new coastlines would be hundreds of kilometers inland from the old. The interior regions of continents, historically less developed with less infrastructure, would suddenly need to absorb populations fleeing submerged coastal megacities. Political systems would fracture under the strain. Resource wars would seem inevitable. Agriculture would face simultaneous catastrophes. the loss of coastal farmland, the disruption of weather patterns that crops depend upon, and the collapse of fisheries as ocean ecosystems collapse. Global food production would plummet at precisely the moment when displaced populations needed it most. Yet even in this darkest scenario, life would persist. Earth has experienced radical climate changes before. The Younger Dryas cooling event 12,800 years ago, triggered by massive meltwater pulses into the North Atlantic, caused temperatures to plummet within decades. Life adapted. Ecosystems reorganized themselves. The planet found new equilibria. But those prehistoric shifts occurred before human civilization, before cities, before nations, before the intricate web of interdependencies that define modern existence. Our thought experiment reveals not just the power of ice, but the fragility of the systems we've built atop a climatically stable world. Lying in the darkness, contemplating Antarctica, it's worth considering what ice truly represents. It is not merely frozen water. It is time made solid. Each layer of ice contains information: the temperature of the year it fell, the composition of the atmosphere, the presence of volcanic ash from eruptions half a world away. Antarctica's ice sheet is a chronicle of Earth's climate stretching back 800,000 years. When we imagine it melting in a day, we imagine not just the loss of ice, but the loss of that archive, the loss of stability, the loss of the climate envelope within which human civilization emerged and flourished. The reality, mercifully, is that such instantaneous melting is physically impossible. Antarctica's ice will persist for centuries, even under aggressive warming scenarios. According to the latest projections from climate scientists, complete melting of the East Antarctic ice sheet, the most stable portion, would require sustained global temperatures 5 to 10 degrees Celsius above pre-industrial levels and would take a minimum of 10,000 years. But our thought experiment serves a purpose. It illuminates the stakes. Antarctica's ice sheet acts as a planetary thermostat, a stabilizing force in Earth's climate system. Its reflectivity moderates temperatures. Its meltwater influences ocean circulation. Its sheer mass affects Earth's rotation and gravitational field. Currently, we lose about 150 gigatons per year, a pace that seems simultaneously glacial and alarming. Glacial because the ice sheet contains 26 million gigatons. Alarming because the rate of loss is accelerating, particularly in West Antarctica, where marine ice sheet instability threatens to trigger runaway retreat. The question is not whether Antarctica's ice will melt. Some melting is already inevitable, committed by past emissions. The question is how much and how fast. The difference between gradual, manageable change and catastrophic disruption lies in the choices made in the coming decades. Antarctica endures, for now, in its ancient frozen silence. 90% of Earth's ice, 68% of Earth's fresh water. A continent of ice holding the memories of 800,000 years and the fate of our future coastlines. The ice remembers. It records. It waits. And in waiting, it asks us, what kind of future will we choose to write into its frozen pages? Or will we, through our actions, ensure that those pages turn to water, carrying their stories into an altered ocean, leaving only the ghost of what once was? Sleep well, knowing that tonight, Antarctica still stands. Its ice still gleams beneath the austral stars. The future, like the ice itself, is not yet written.